Based on the nature of the reaction, redox reactions are divided into 4 types. These are combination reactions, decomposition reactions, displacement reactions, and disproportionation reactions. Let's look at each type of the reactions. As the name implies, a combination reaction is a chemical reaction in which 2 or more substances combine to form a single new substance. A combination reaction can be represented as A plus B gives rise to C. For a combination reaction to be a redox reaction, either A or B or both should be in elemental state. We know from the oxidation number rules that atoms of elements in elemental states have an oxidation number of 0. Thus, when substances with 0 oxidation number combine, one substance will be oxidized and the other will be reduced. Let's look at some examples of redox combination reactions. Carbon and oxygen in elemental states combine to give carbon dioxide gas. The oxidation number of carbon and oxygen is 0. When carbon dioxide gas is formed, the oxidation number of carbon becomes +4 and oxidation number of oxygen becomes -2. Here, carbon undergoes oxidation. As its oxidation number increases from 0 to +4. Simultaneously, oxygen undergoes reduction, as its oxidation number decreases from 0 to -2. Magnesium reacts with nitrogen to give magnesium nitride. In this reaction, the oxidation number of magnesium changes to +2 from 0, as it is oxidized. Simultaneously, the oxidation number of nitrogen changes from 0 to -3, as it is reduced. Now let's look at decomposition reactions. Decomposition means breakdown. Thus, a decomposition reaction is a chemical reaction in which a compound breaks down into 2 or more substances. It is the opposite of combination reaction and can be represented as shown here. For a decomposition reaction to be a redox reaction, it is essential that at least one of the product of the decomposition reaction is in the elemental state. One of the most common examples of a decomposition reaction is the breakdown of water into hydrogen and oxygen. The oxidation number of hydrogen decreases from +1 to 0 as it gets reduced, while oxidation number of oxygen increases from -2 to 0 as it gets oxidized. Note that as the products, hydrogen and oxygen of this reaction are in the elemental state, it is a redox decomposition reaction. In this example, potassium chlorate decomposes to form potassium chloride and oxygen. One of the 2 products, oxygen, is present in elemental state. Hence, this reaction is a redox decomposition reaction. The oxidation number of chlorine decreases from +5 to -1 as it gets reduced, while oxidation number of oxygen increases from -2 to 0 as it gets oxidized. Note that there is no change in the oxidation state of potassium. Now, consider the decomposition of calcium carbonate. The products we get are calcium oxide and carbon dioxide. As none of the products are in the elemental state, and as there is no change in oxidation state of any element, this reaction is not a redox decomposition reaction. The third category of reactions is the displacement reactions. In a displacement reaction, the atom or ion in a compound is replaced by the atom or ion of some other element. The reaction can be expressed as X plus YZ converts to XZ plus Y. In this reaction, from the compound YZ, Y has been displaced by X. Displacement reactions are of two types: metal displacement reactions and non-metal displacement reactions. In a metal displacement reaction, the metal in a compound is displaced by some other metal in the elemental state. For example, in this reaction, copper sulfate reacts with zinc to form copper and zinc sulfate. This is a displacement reaction because copper has been displaced by zinc. The oxidation number of copper has decreased from +2 to 0. Hence, copper is reduced. Simultaneously, the oxidation number of zinc is increased from 0 to +2. Hence, zinc is oxidized. Thus, the reaction as a whole is a redox displacement reaction. In this reaction, titanium tetrachloride and magnesium react to form titanium and magnesium chloride. As you can see, magnesium has replaced titanium to form magnesium chloride. The oxidation number of titanium has changed from +4 to 0, and magnesium from 0 to +2 oxidation state. Thus, this reaction is also a redox displacement reaction. Similarly, in this reaction between chromium trioxide and aluminium, aluminium replaces chromium to form aluminium oxide. In each of the metal displacement reaction, a metal displaces another metal, and the reducing metals like zinc, magnesium and aluminium are better reducing agents than copper, titanium and chromium. That is, the metal being reduced. The second type of displacement reaction is the non-metal displacement reaction. In a non-metal displacement reaction, a metal or a non-metal displaces another non-metal in a compound. In most non-metal reactions, the non-metal displaced is hydrogen. However, some reactions involve displacement of oxygen or halogens. Let's look at examples of metals displacing non-metals. All alkali metals and certain alkaline earth metals displace hydrogen from cold water. For example, sodium, an alkali metal, displaces hydrogen from cold water to give dihydrogen gas. Similarly, calcium, an alkaline earth metal, reacts with cold water to displace hydrogen. less reactive metals like magnesium and iron react with steam to produce dihydrogen gas. For example, magnesium reacts with steam to produce magnesium hydroxide and hydrogen gas. Similarly, iron reacts with steam to form iron 3 oxide and hydrogen gas. Many metals, including those that do not react with cold water, can displace hydrogen from acids to liberate dihydrogen gas and the respective salt. For example, zinc reacts with hydrochloric acid and displaces hydrogen to form zinc chloride and dihydrogen gas. Similarly, magnesium and iron react with hydrochloric acid and displace hydrogen from hydrochloric acid to liberate dihydrogen gas along with the formation of magnesium chloride and iron chloride respectively. Very less reactive metals like silver and gold do not react with hydrochloric acid and hence cannot displace hydrogen. We learnt about the activity series of metals and saw that zinc releases electrons to copper and copper releases electrons to silver. Similarly, halogens also have an activity series. The halogens in 17th group include fluorine, chlorine, bromine, and iodine. These halogens have a tendency to accept electrons as they need an electron to complete their octet. This tendency causes them to be reduced. Hence, they are good oxidizing agents. The oxidizing power of these halogens reduces as we move down group 17, with fluorine being the highest and iodine being the lowest. Fluorine is highly reactive and can displace chloride, bromide, and iodide ions in a solution. Due to its high reactivity, it can also displace oxygen from water. Therefore, displacement reactions of chloride, bromide, and iodide ions with fluorine are not carried out in aqueous solutions. Let's look at some more halogen displacement reactions. In these reactions, chlorine displaces bromide and iodide ions from the aqueous solutions of their salts. These reactions are used to identify bromide and iodide ions as the bromine and iodine produced have characteristic colors. This identification is called as layer test. Similarly, bromine can displace iodide ions in an aqueous solution. Halogen displacement reactions are used in industrial applications to produce chemicals, such as hydrofluoric acid, which is used to etch glass. Did you know that while there are a number of oxidizing agents that can oxidize chloride, bromide, and iodide ions, no oxidizing agent is available to oxidize fluoride ions? This is because fluorine is the strongest oxidizing agent. The only way to prepare fluorine is to oxidize fluoride ion electrolytically. Finally, let's look at the last type of reaction, disproportionation reaction. A disproportionation reaction is a reaction in which the same element is oxidized as well as reduced. For such reactions to occur, one of the reacting elements should exist in at least 3 oxidation states. For example, the decomposition of hydrogen peroxide is a disproportionation reaction. Here, oxygen has a -1 oxidation number in hydrogen peroxide. It gains electrons and increases to 0 in O2 and decreases to -2 in water. Here is a disproportionation reaction that illustrates the preparation of household bleaching agents. In this reaction, hypochlorite ion, which shows bleaching action, is formed by dissolving chlorine in alkali. Chlorine, having an oxidation state of 0, is being reduced to -1 in chloride ion and also being oxidized to +1 in hypochlorite ion. Note that, like chlorine and bromine, iodine also undergoes disproportionation. However, fluorine with alkali does not show a tendency to undergo a disproportionation reaction. This is because fluorine is the most electronegative element and hence cannot exhibit any positive oxidation state.